How about now? I think you should be able to hear me now. Great, awesome. I don't know why it won't like auto default to that. It's kind of frustrating. But I don't see a way to make that the default choice. So I guess we'll just live with it. All right. Sharing the screen. Sorry, it's like I guess the sun in your eye is terrible. It's not that bad as far as things in your eye go. Like it's not, but it doesn't feel great. In case you're wondering why I'm blinking oddly. Okay, get rolling here. Talking more about some Taylor series. So we have class today, we have class Wednesday, and then there's final start Friday. So I think the plan is to do some sort of reviewing on Friday. I know someone was asking me like if I would have thought the final would consist of as far as like how much of this last material. It's not a question I have a good answer to, but I do think your professor could probably answer that. So as far as like how much from the first midterm, how much from the second, how much of this Taylor power series stuff but I don't know. My guess would be, I really don't. Let's see, Co-16C, today is June 3rd. It's June already. All right, so last time, and then we were kind of talking about how, at least my opinion is, when you're finding a Taylor series, you kind of have one of two directions to go. You can either use Taylor's formula, or you can use the known Taylor series and manipulate it. Those are kind of the options. And so just as a reminder, the ones that we kind of know so far, I know we wrote this down last time, but I'm gonna write it down again. So some known Taylor series. The following. So you have e to the x, 1, these are not written in any specific order, these are just the order I think of them in. 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. That's the sum from n equals 0 to infinity of x to the n over n factorial. The center is 0. The radius of convergence is infinity. This series converges everywhere. Same is true for sine of x, which is all the odd terms. So one thing I do think about for these ones specifically, e to the x sine and cosine, is that sine and cosine have all the terms of e to the x. It's just that they alternate. So sine is all the odd power terms. So it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. And then we write that as the sum from n equals 0 to infinity of x to the 2n plus 1 over 2n plus 1 factorial times negative 1 to the n. Center is 0, radius is infinity. Same is true for cosine, so now cosine is all the even powered terms. So it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And that's the sum from n equals 0 to infinity of x to the 2n over 2n factorial times negative 1 to the n. Same center, same radius. And then we have a couple others. Here are the maybe 3 or 4 other ones I would probably recommend. So the next one I think about is 1 over 1 minus x, which I would really, when you see that, I would like you to think of the words in your head. It's the first term divided by 1 minus the ratio. it's the sum of the geometric series. It's, watch this, it's the first term divided by 1 minus the ratio. Oh, so the ratio has to be x here. So every subsequent term is just multiplied by x. So 1 times x is x. X times x is x squared. X squared times x is x cubed, and so on. This is just the sum from n equals 0 to infinity of x to the n. The center is still 0. The radius of convergence here is 1. I don't usually memorize this next one, but it does come up, and it is written in her, like I was looking at her notes from, I think, Friday, and it certainly is one of the ones that shows up like in the little textbook section that she often shows you, which is 1 over x plus 1. I would never write it that way. I would write 1 over x plus 1 as 1 over 1 plus x, and then I would really imagine it as 1 over 1 minus x. Or again, my first term divided by 1 minus my ratio. So this is going to be my first term 1 plus my 1 times the ratio is negative x. And then my next term is going to be x squared, and then minus x cubed, and then plus x to the 4th. That's going to be the sum from n equals 0 to infinity of negative 1 to the n times x to the n. Yeah, that's how I would write it.
You said 1 over minus, or over 1, first term over 1 minus the ratio.
Right. I should say if it looks like that, right? Obviously, I think cosine, sine, and e to the x are never going to look like a first term over 1 minus the ratio. But if you see something fractional, it's often a good idea to try and think about writing it like this. Doesn't always work out, but it sometimes works out. And then the other one that is probably one that comes up relatively often are the following two. So let's start with natural log of x. Centered at not 0. So if it's centered at 0, well, natural log of 0 is undefined. So a series should never be undefined, centered where it's undefined. So it's centered at c equal to 1. Oh, by the way, that previous one also, the center was 0, yeah. And the radius is 1. So for this natural log of x, we don't know what it actually is. Like we don't know Taylor series, so we're going to do it the long way. The finding all the derivatives and finding a pattern for the derivatives and that kind of deal. So let's start writing out some derivatives. First derivative is going to be 1 over x. It's always a good idea to write your derivatives in a way that it's easier to take the next derivative. So let's write that as x to the negative 1. And then my second derivative is going to be negative 1 times x to the negative 2. We can see that things are going to alternate signs. My third derivative is going to be positive 2 times x to the negative 3rd. I'm going to start not simplifying things, meaning I'm not going to write negative 6 for my next coefficient. I'm going to write that the fourth derivative is really negative 3 times 2 times x to the negative 4th. Because when I write it that way, it starts to make me think I might have some sort of factorial thing going on. Because 3 times 2 is the same as 3 times 2 times 1. And that is 3 factorial. And if I look at the next one, it looks like my fifth derivative is going to be positive 4 times 3 times 2 times x to the negative 5th. And then I kind of like to do a gut check kind of thing. I'm like, okay, I think I see the pattern. I don't want to try and write down the nth term just yet because I feel like that can be a little bit extra challenging. Let's try and write down like the 10th derivative. So the 10th derivative of x, I'm not going to write out the sign. I'll figure out the sign in a second. So if my fifth derivative was 4 times 3 times 2, and my fourth derivative was 3 times 2, I'm expecting my 10th derivative to start at what number? 9. Yeah, I don't know if it's negative. It might be negative. You might be right. I don't know. I think you're right because it looks like the even terms have the negative ones. So let's go ahead and say it's negative 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. What I really should be writing here is 9 factorial times x to the what power? Negative 10. Yep, right on. I think that's great because then I think it's easier to see then that the nth derivative at x is going to be n plus 1 factorial. Nope, 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 nope. Not n plus 1. 10 plus 1 is not 9. Scratch that. It's going to be n minus 1 factorial times x to the n, negative n. Holy smokes. This is why it's good to write the pattern before the thing for it. And then it looks like if n is even, we want a negative, and if n is odd, we want a positive. So we need a negative 1 to the, you can do n plus 1 or n minus 1. Either way will give you a negative when it's even and a positive when it's odd. So I would probably do negative 1 to the n plus 1. It doesn't really matter though. And then we want to see what we're getting when we plug in 0. Sorry, not 0, when we plug in our center, which is often 0, but it's not 0 here. So we look at plugging in 1, f prime of 1 is just 1. F of 1 is 0. You should always do the first one too, right? If you plug in 1, you get 0. F double prime of 1 is going to be negative 1. F triple prime of 1 is going to be positive 2 factorial. The fourth derivative is going to be negative 3 factorial. The fifth derivative is going to be positive 4 factorial. It looks like our nth derivative at 1 is going to be negative 1 to the n plus 1 times n minus 1 factorial. Because the 1 to the negative n, 1 to n power is 1. Which is why you're centering this thing at 1, because it works out nicely. So then we throw this all into the Taylor's formula. So Taylor's formula says that, I'll remind you that here's the general formula, that your function f of x is equal to the sum from n equals 0 to infinity of your nth derivative evaluated at your center divided by n factorial times x minus your center to the nth power. So we have everything we need to fill in the blanks. I will point out, when we're doing this, this top part here, this nth derivative evaluated at your center, is the only thing you actually have to find. Everything else is kind of just there. The bottom is just n factorial, and this part here is just x minus whatever they told us the center was to the nth power. So here, we're going to write this as the sum from n equals 0 to infinity of negative 1 to the n plus 1 times n minus 1 factorial over n factorial times x minus 1 to the n. And then we should simplify this. N minus 1 factorial over n factorial becomes just 1 over n. Interesting. So there's something to say here. There is something to say here. Yeah, what is the thing I'm trying to say here? Good question. So what I should have pointed out, is that in this case, if you plug in n equal to 0, the 0th derivative at 1, which is the original function, is just 0. Right? F of 1 is 0. Natural log of 1 is 0. So this really shouldn't start at 0, because if we start at 0, we're not going to get a term. So we actually need to start at 1. Also because starting at 0 formulaically is problematic. You end up getting a negative factorial, which is a problem. So we should really be starting at n equals 1, and then it's easier to simplify this as the sum from n equals 1 to infinity of negative 1 to the n plus 1. n minus 1 factorial over n factorial just becomes division by n times.
So should the n equals 1 on the top one as well?
Well, so not exactly, because this is the general formula for any Taylor series. But for this Taylor series specifically, since the n equals 0 term would just be that the derivative, the function was equal to 0, we eliminate that term. We don't write it, so we just start one term later. But yeah, that's a fair question you're asking. Yeah. Sometimes it's less problematic because you're not like weirdly dividing by 0, but here you kind of are. In case everyone, just to make sure everyone's clear here, the reason this is simplifying like this is because n minus 1 factorial or n factorial that denominator is just n times n minus 1 times n minus 2 times n minus 3, which is just an n minus 1 factorial. It's kind of like saying 17 factorial divided by 18 factorial. If you're right at the top, it's 17 times 16 times 15 all the way down. If you're at the bottom, it's 18 times 17 times 16 times 15 all the way down. And everything cancels except for the 18 on the bottom. So that's 1 over 18. Similarly here, this is just going to be 1 over n. That's where that's coming from. So to add to our list of things that come up frequently, I will first say, like, I don't memorize this one. I don't have this one memorized. It's just not in my wheelhouse of things that are like there. But it is worth knowing that the natural log of x is equal to the sum from n equals 1 to infinity, of negative 1 to the n plus 1 over n times x minus 1 to the n. Yeah. If you want to write out some terms, that would be, let's see, the first term, if I plug in n equals 1, is going to be x minus 1. And then it's going to be minus, right, because we're going to change signs, x minus 1 squared over 2 plus x minus 1 cubed over 3. It just keeps going on and on like this. Minus x minus 1 over 4, da, da, da. I imagine from looking at the notes that there hasn't been any discussion or talk about like taking the derivative of a Taylor series. That's fine if there hasn't been. Like my expectation is you have not talked about that. Oh, the remainder. Okay. All right. Okay. Because so here's what I want to say is you could also find the Taylor series for like 1 over x. And one way people do that sometimes is by taking the derivative of this series.
We did two intervals.
Oh, sure. Yeah. But that's kind of, yeah, I know what you're saying, and that's a thing. But we're typically not using the integral to find a new Taylor series. We're using the integral to like calculate something, which is totally fine. But like, so yeah, I'm just trying to prevent myself from saying things I don't really need to say because you don't need to hear them because you're not gonna, like, it's not something you should worry about. Although it's kind of cool. So if I wanted to find the Taylor series for like 1 over x, for example, well, again, we don't really, so this is where things get a little bit weird. Yeah, I like that. So there's 2 ways you could go. You could go the formula route, the Taylor's formula route. Surprised some math person hasn't tried to make up like a Taylor's formula, kind of like to do something fun with that. I could see someone trying to make that work. Not very well, probably. Or you could go with the manipulating things you know direction. Okay, so let's talk briefly about using Taylor's formula because it's going to be similar to what we just did. Because really, we're just starting off 1 step later, right? If you look back at our previous list, the derivative of natural log of x was 1 over x. And then you have all, so really, I think we can almost just say it's practically the same. You're just kind of cutting off a term. Yeah, you really are. That's super cool. I never thought about that. That's interesting. Let's see. So if we start here, right? Again, we're not centering at 0 because centering at 0 would be problematic. It's undefined at 0. But if we're centering at 1, well then, we already know the pattern, right? Our function is 1 over x to the negative 1. Our first derivative is negative x to the negative second. Our second derivative is positive 2x to the negative third. And so on. Our third derivative is negative 3 factorial x to the negative fourth. It looks like our nth derivative is going to be, well, now the numbers are matching with the factorial, so it's going to be an n factorial. And we're gonna have a negative when it's odd, a positive when it's even. So we want a negative 1 to the n, and then an x to the negative 1 more than n. So it looks like our nth derivative evaluated at our center is going to be negative 1 to the n times n factorial. And then throwing this into Taylor's formula, we're going to get that 1 over x is equal to the sum from n equals, we are going to start at 0 this time because, right, starting at 0 doesn't cause a weird problem. And if you look, the function at the 0th derivative, which is the function evaluated at 1, right? F of 1 is just 1. So there's not like a weird potential division by 0 thing. From n equals 0 to infinity of our nth derivative, which is just negative 1 to the n times n factorial over n factorial times x minus 1 to the nth power. Yeah. The n factorials cancel. And this becomes the sum from n equals 0 to infinity of negative 1 to the n times x minus 1 to the n. If you start writing out terms, you get 1, because negative 1 to the 0 is 1, and x minus 1 to the 0 is 1, and then minus x minus 1 plus x minus 1 squared minus x minus 1 cubed, and it goes on and on and on, which is the formula you see in the textbook. But I would argue that there's an easier way. So another way to do this, whoops, didn't mean to cross that out like that, sorry, is to manipulate something you know. So I'll remind you all that we know 1 over 1 minus some ratio is equal to 1 plus that ratio squared, plus that ratio cubed, and so on, which ends up being the sum from n equals 0 to infinity of that ratio to the nth power. So I'd really like to rewrite this as 1 over 1 minus something, because that's super nice for us. So 1 over x, we could write as 1 over 1 minus something. Let's see, I want to subtract something, so I'm left with x. Well, I could actually just do the algebra. I could say x equals 1 minus whatever, and then solve for whatever. Whatever plus x equals 1, the whatever is 1 minus x. So that's what needs to go in there. X equals 1 minus 1 minus x. So that's what's going to go in here. And so then we have 1 over 1 minus a ratio. And we can literally, and I've kind of left myself not the right amount of room here, sorry. Our 1 over 1 minus a ratio is equal to the first term plus the first term times the ratio, and so on and so on and so on. So it looks like the sum from n equals 0 to infinity of 1 minus x to the nth power, which might not look like it's written exactly the same way, but these are exactly the same thing. This here and this here are the same, right? 1 plus 1 minus x plus 1 minus x squared is the same as 1 minus x minus 1 plus x minus 1 squared. We're just multiplying the negative 1 by the x minus 1 to get 1 minus x. Same. I think it's kind of cool that you can find these two things in totally different ways.
So what's the ratio? Oh, it's the, what's the 1 over 1 minus.
The ratio here is just the 1 minus x. So yes. What else to say here? Oh yeah, there's this one other one. I know. Okay. But this one comes, yeah, not my favorite. So there's one more that you should be aware of, I think, because it definitely, I saw some problems where it comes up. So the last one we should be aware of here is the binomial. I think that's what it's called. Yeah, the binomial Taylor formula. I don't think anyone should ever have to memorize this one. It's in the book. Here's what it is. You have 1 plus x to the k is equal to 1 plus k times x. And here's how the pattern kind of works. Each subsequent term, you multiply by one more thing that's less than k and divide by one more term. So like the next one's going to be k times k minus 1 divided by 2 factorial. Yeah, that's right, times x squared. The next one, we're going to increase the factorial and increase the number of terms on top. So we're going to have k times k minus 1 times k minus 2 over 3 factorial times x to the third. And then we just keep going. The next one would be k times k minus 1 times k minus 2 times k minus 3 over 4 factorial times x to the fourth. And there's not really a good way to write this as a series, like with the sigma notation, so we usually just write it like that. And I should point out that the interval of convergence here is -1 to 1. Which means that the radius of convergence is 1. So what did I want to do with this? Yeah, I want to do that instead. Let's grab that. Yeah. So sometimes we use Taylor series to then try to approximate some sort of integral, because there are lots of functions that are not integrable, or that's the wrong word. Functions that we can't find an antiderivative for, so we can't use the second part of the fundamental theorem of calculus to be like, oh, it's the antiderivative, you plug in the top point, minus you plug in the bottom point. So what we do instead is we find a Taylor approximation. Let's look at this example. So here's an example of something we might do. We're going to use a 5th degree Taylor polynomial, which just means x to the 5th is the highest power of x we should see. We might not get that high, right? If your series was like x squared plus x to the 4th plus x to the 6th, we wanted a 5th degree, we would cut it off to x to the 4th. 5th degree Taylor series to approximate the integral from 1 to 2 of the natural log of x squared plus 1 over x squared. Interesting. So we're going to find a Taylor series for this. Now, here's what I would do. I would find some of the terms for natural log of x squared plus 1. So especially when you're only finding a few terms, it's usually the right kind of idea just to go with the long form formula. So like for natural log of x squared plus 1, my first derivative is going to be 1 over x squared plus 1 times 2x. Well, this is looking kind of gross. I don't know if I like the way this is going. Yeah, I probably wouldn't do that. Yeah, so let's talk about how this is going to be terrible in a second. So this is 2x over x squared plus 1. My next derivative is going to be, yeah, I don't like this at all. Bottom, there's the top minus top. There's the bottom, all over the bottom. This seems like it's going to get out of hand real quickly. So what do we do instead? This is where we're using what I think of as like the not substitution like U substitution, but the substitution method for finding Taylor series. Here's what I mean by this. So we know that the natural log of x centered at 1, we just found it a minute ago. That's going to be, if I remember, we just found it a minute ago, he says, while not remembering what it is at all. It's one that's never stuck in my head appropriately. Natural log of x was that. Interesting. So here's the natural log of x. It's your good old x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3, and so on and so on and so on. So what we're going to do is we're going to take that series and we're going to replace the argument x with x squared plus 1, which is kind of weird, but is totally valid. So the natural log of x squared minus 1, we're going to replace each x with x, of natural log of x squared plus 1. We're going to replace each x here with the argument x squared plus 1. Because this is going to be x squared plus 1 minus 1 minus x squared plus 1 minus 1 squared over 2 plus x squared plus 1 minus 1 cubed over 3 minus et cetera, et cetera, et cetera. Let's simplify that because we can make it look a lot nicer. That's the natural log of x squared plus 1. It's going to equal to x squared minus x squared squared over 2 plus x squared cubed over 3. Let's tack on one more term just to make sure we have enough terms. Minus x squared to the 4th over 4. And then we're going to divide each thing by x squared to get the actual thing we want. So natural log of x squared plus 1 over x squared is just 1 over x squared times all of that, which is just going to decrease each term's power by 2. So that's going to be 1 minus x squared over 2 plus x squared squared over 3 minus x squared to the 3rd over 4. We probably don't need that last term there. Because again, we're trying to just use a 50 Taylor polynomial. So we're going to use these first 3 terms to approximate the thing that we're integrating. So here's what we're going to get. We're going to have the integral from 1 to 2 of natural log of x squared plus 1 over x squared dx is approximately equal to the integral from 1 to 2 of 1 minus x squared over 2 plus x to the 4th over 3. So that's the idea of what we're doing. We're saying we can make this integral, or we can approximate this integral with something much, much, much easier to find the antiderivative of. Because powers of x are always relatively easy to find the antiderivatives of. So then this is going to be x minus x cubed over 3 times 2 plus x to the 5th over 3 times 5 from 1 to 2. We plug in 1 and 2. I should say we plug in 2 and 1. So we get 2 minus 8 over 6 plus 32 over 15 minus 1 over 6 plus 1 over 15. And I would not simplify that further. Probably. That's 2 minus 1 is 1. Negative 8, 6 plus 1, 6 is negative 7, 6. And 32 over 15 minus 1 over 15 is 31 over 15. I don't think there's a lot of value in going any further than that, though. Sorry. Sunscreen killer. I should ask, did you talk about like bounding the error on things like this? Because I know you mentioned the remainder. I don't think so. Yeah. Okay.
Why does just plugging it in to like the other equation work, even if like normally the x squared would make them very different?
So yeah, that's a really, really fair question. Let's look at this slightly. Yeah, let's look at a slightly easier example to kind of see why that's true. So let's say, yeah. So things are going to get messy here. You probably don't need to write this all down, but you always want to. So let's say that we wanted to find the Taylor series for something easy-ish, like f of x equal to e to the x squared. And we could, and we will do it the long way. But I will tell you that the short way is first, note that g of x equal to e to the x. We know the Taylor series for that. It's going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on. It's the sum from n equals 0 to infinity of x to the n or n factorial. So one way to think about what's happening here is that f of x, which is e to the x squared, is really just g of x squared. And g of x squared is, well, everywhere we see an x, we're just going to replace it with an x squared. This is what I mean by the substitution method for these Taylor polynomials. So we can say that's going to be 1 plus x squared plus x squared squared over 2 plus x squared cubed over 3 factorial. And we're even doing it here. We're replacing the x there with x squared. Which you would then write as x to the 2n over n factorial. Or I should say the sum from n equals 0 to infinity of x to the 2n over n factorial. Quick reminder, 0 factorial is equal to 1. 1 factorial is also equal to 1. Actually, I know it's a little weird. It's kind of like how 3 to the 0th power is equal to 1. 0 factorial is defined to be equal to 1, so that we don't have weird division by 0 problems. So, okay, here's where it's probably going to get a little bit messy. Let's actually try doing this the long way. So we're going to take a few derivatives here, regretfully. So f of x is e to the x squared. The first derivative is e to the x squared times 2x. The second derivative, okay, product rule. It's the derivative of e to the x squared, which is in itself e to the x squared times 2x times the other 2x plus e to the x squared times the derivative of 2x, which is 2. And I think it's going to be most advantageous to us if we factor out the e to the x squared. So let's rewrite this as e to the x squared times 4x squared plus 2. Okay, let's keep going. Third derivative is going to be derivative of e to the x squared, which is e to the x squared times 2x times the other stuff left alone, plus, switch it up, leave the e to the x squared alone, and the derivative of 4x squared plus 2 is 8x. Factor out the e to the x squared, and you're left with, okay, let's be careful here, a 4x squared times 2x, which is an 8x cubed, and then a 2x times 2, which is a 4x, plus an 8x, which is going to be a 12x. I know things are, so as you might notice, this is why we try to not do it this way if we can help it, because it gets messy fast. Let's give ourselves 1 or 2 more terms. So the fourth derivative here is going to be derivative of e to the x squared. One more time is e to the x squared times 2x. You leave the other stuff alone. Plus, now you leave the e to the x squared alone, and the derivative of 8x cubed plus 12x is 24x squared plus 12. Factor out the e to the x squared. Let's see. So here you've got a 2x times 8x cubed, which is a 16x to the 4th. A 2x times 12x, which is a 24x squared. Plus another 24x squared is a 48x squared. And then plus a 12. We'll do one more. So the fifth derivative here is going to be, okay, e to the x squared times 2x times all that. And if we worked hard enough, we might be able to figure out a general pattern for the nth derivative. I think it would be really, really challenging, though. And then the other part of the product rule, e to the x squared times the derivative of all this, which is 16 times 4 is 64, x to the 3rd, plus 96x plus 0. Factoring out the e to the x squared, 2 times 16 is 32x to the 5th. 2x times 48x squared is going to be a 96x cubed plus a 64x cubed is 160x cubed. And a 2x times 12 is a 24x plus a 96x is going to be 120x. So first, notably, every odd derivative, first, third, and fifth, have a factor of x. So that when we plug in 0 for the center, all those terms aren't going to give us a term. Which makes sense, because when we write this out, the e to the x squared, you only have even powers of x showing up. So that seems reasonable. So let's actually take a look and see what we get. So if we try to write this out, just using what we've got, e to the x squared should be, well, it's going to be I'm going to write out the general formula. It's going to, let me back up for 1 second. Apologies. So f of x, writing out the Taylor formula, but kind of the long way, is going to be your f of 0 plus f prime of 0 over 1 factorial times x minus 0 to the first plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x to the third, and so on and so on. So actually writing out terms. So f of 0 is 1. F prime of 0 is 0. Doesn't matter what the rest is. F double prime of 0, if I haven't made a mistake, is e to the 0 times 0 plus 2, which is 2, over 2 factorial times x squared. F triple prime of 0 should be e to the 0 times 0 plus 0, 0. F, the fourth derivative of 0 is going to be e to the 0 times 0 plus 12 over 3 factorial. I'm a little worried there. I'm not worried. I'm okay. Times x to the fourth. I should have gone one more derivative, but I didn't. The next term is 0. So if we look at the first terms we've got here, let's take a look. My 1 matches the 1. My 2 over 2 factorial is 1 times x squared. My 12 over 3 factorial is, I am a little concerned here. Bless you. My 12 over 3 factorial is not right. What mistake did I make? So here's what I'm seeing here. I should be right. It should be x to the fourth over 2, and I'm getting 2 times x to the fourth. What did I forget about? Darn it. I was really like, this is going to work just fine. Yeah, what am I missing? Oh, no. Go ahead.
64 cubed plus 60, like for its absolute bit, right?
I'm looking at the fourth. I'm looking at this one right here. Yeah. If I plug in 0, and because I'm looking at this term here, which should be my fourth derivative at 0 divided by 4 factorial, not 3 factorial. And 4 factorial is 24, and 12 over 24 is 1/2, as it should be, right? Because this term here is x to the fourth over 2. This term here is x to the fourth over 2. So hopefully this is kind of displaying to you, Heather, one, that it is right? That we're, not just Heather, everybody, that it's right, but also that it is tedious and terrible to do it this way. So we can, in fact, say, well, this function that we have the Taylor polynomial for, we can just substitute in kind of whatever we want for x, and it still works. It's kind of weird, but it does work. So yeah, it's a little bit strange because I think the other example was a little bit more complicated, but it is really true. Like that if you take, for example, so we were talking about the natural log of x being, I can't remember, it's impossible. I think it's 1 minus x minus 1. All of them? I'm not sure which ones you're responsible for memorizing.
I think she said that if we absolutely need one of the ones that were in the textbook that she showed us, she would provide it to us.
Okay.
But she said that maybe she didn't spend over the course of doing all the homework, we're gonna end up referencing give you the next one.
Right. I would say for me, I would expect people to know e to the x, sine of x, and cosine of x. Those are the ones that always stick out in my head. No, I've got the, why do I? Why is that different? So I've written the wrong thing and it's perturbing to me. Sorry. For the thing I just wrote there, that is off by a moment. Yeah, that's the wrong. That's what 1/x is. Not quite. No, that's nothing good at all. Sorry. I started with the wrong term here. Why is just spend some time practicing them. So what we were saying natural log of x is x minus 1 minus x minus 1 squared 2 plus x minus 1 cubed over 3. And then we use this to find the natural log of x squared plus 1. And it really is okay just to say, well, for every x, we're just going to input an x squared plus 1. Again, you could try to find these terms, but it gets extremely messy, right? The first derivative here, what's time? I have not enough time. The first derivative is 2x over x squared plus 1. The second derivative is going to be, wow, yeah, bottom, go to the top minus top, go to the bottom, all over the bottom squared. And it's going to get just gross fast. Yeah. 2 minus 2x squared over x squared plus 1 squared. Yeah, I don't even, sorry. So I should just say, this is why we're trying not to do it this way. Because if you can do it a different way, you should. But then there are some functions that you just can't. Like there are some things that are not recognizable as something we know. So we just appeal to the usual long form of Taylor's formula. But if you are hit with something like, find the Taylor series for sine of x cubed over 2, we should just take the Taylor series for sine of x and replace the x with x cubed over 2. So we know that sine of x is equal to x minus x cubed over 3 factorial, right? Just every odd power. And then so sine of x cubed over 2 is just x cubed over 2 minus x cubed over 2 cubed over 3 factorial plus x cubed over 2 to the 5th over 5 factorial, and so on and so on and so on.
Thank you.
You're welcome. That's all I should really say because it's about 2 o'clock. We meet on Wednesday. We can talk more about Taylor series stuff, but we can also talk about more stuff if you want. And then your final is on Thursday of finals week? No.
I think it's Tuesday.
Okay. I think it was June 11th. Sounds right. Which is Tuesday. So I will try to write up some sort of practice final before the end of this week. Get it posted. Yeah. See you on Wednesday. Do you fill out the attendance form when you have a minute? I do have a QR code here if you want to scan it, but you can also just do it later if you prefer.